Okay, thank you very much, Gabriele, and thank you for the invitation to give this webinar, and hello to everybody, whatever the time of the day in your country, indeed. So this work on electronic structure, including electron-phonon effect, that I will present has been done in the last couple of years with numerous collaborators who are listed here, not even all of them. But I would like to motivate, to motivate this work. It is well known that electronic properties of material and optical properties of material do depend on the temperature. Let's take one example. As a function of the photon frequency comes the dielectric response, the imaginary part of optical response of germanium. And you see that as a function of the temperature, the peaks shift in energy, going from 100 Kelvin to 825 Kelvin, and also broaden with increasing temperature, which means a decreased electron lifetime. But even at 0 Kelvin, the vibrational effects are important due to zero-point motion. And for the diamond band gap, optical measurements of absorption give the following points here. With decreasing temperature, one will obtain this limit, but actually by interpolating the high temperature behavior, one can infer that without any movement of the nucleus, the limit should be this one here, with 0.4 EV difference with respect to the experimental value. So this 7–8% change of the band gap is strictly due to the fact that even at 0 Kelvin, the fluctuation of the atomic positions cannot be ignored. And usually this effect is not included in first principle DFT or beyond calculation. And it is also linked to the formation of polarons, as I will explain in the latest part of the talk. My talk is actually structured as follows. First, we will look at the effect of vibrations on the electronic structure from different perspectives and methodologies. Then I will show you immediately the comparison between theory and experiment in the one methodology that I favor. Actually, I will show that the so-called adiabatic approximation has trouble to predict correctly the zero-point normalization of material. And in this respect, I will discuss the adiabatic quadratic approximation divergences, both from the math and the physics point of view. I will connect with the Fröhlich model, a workhorse for the description of polaron. And then I will discuss also the limitations of the Fröhlich model and or perturbative approaches. I will mostly base my presentation on these 4 recent papers, but there are also some older papers that I will mention throughout the webinar. Let's look indeed at the different methodologies that can be used to integrate the effect of vibrations inside the electronic structure. I start with very simple system. The H2 molecule and the CO molecule, they have each highest occupied molecular orbital eigenvalue, and I will represent this eigenvalue, as a function of the bond length for these two molecules, bond length variation. Of course, I take as reference the equilibrium bond length. I put the 0 of eigenenergy here at this zero modification of bond length, and I'm looking at the modification of the eigenenergy as a function of the bond length. There is clearly a linear part, but also a small quadratic part. This is both for H2 and for CO. And actually, with the vibrations coming in beyond the frozen atomic position, electronic eigenenergies change with the bond length, and this can lead to a broadening of the eigenenergy position, and so spectroscopic values, and also a shift. The broadening in this simple picture will come from the linear behavior of the eigenenergy with respect to the bond length, but the shift of the average position will come from the curvature, the second order derivative. If one explores a larger and larger bond length, then there will be globally a modification of the average position of the eigenenergy. In this very simple approximation, nevertheless, one can consider more complex system than molecules, and one can imagine to examine molecular dynamics trajectories with time at average temperature, and get this eigenenergy as a function of the temperature by taking the limit for long time of the average eigenenergies position. It's a well-defined procedure. It is compatible with current implementations and computing capabilities. These eigenenergies might be taken from density functional theory or GW approximation, which is a much better way to obtain eigenenergies. Anharmonicities might be included in these molecular dynamic trajectories, but there are some problems with such a simple approach. If we use classical dynamics, there is clearly no zero-point motion. At zero temperature, the atoms are frozen. And also this methodology makes the adiabatic approximation in the sense that the electron immediately adjusts to the position of the nucleus. So actually there are vibrations, but there is no exchange of energy between the phonon and the electron system. It might also become hard to apply methodology for solids because we have to use supercells, and this is because phonon wave vector wavelengths can be not periodic with the same period of the small periodic cell of defining the solid. And this supercell will mix eigenstate, and we might need unfolding of the band structure for this large supercell. But let's ignore this orange problem in this talk, because there have been good technologies, good techniques to deal with this problem. These two problems in red are much more important. Let's try to wave the zero-point motion, well, the classical dynamics description of the phonon in order to obtain the zero-point motion. Then what one can do is the thermal average with quantum vibrational states. This involves the partition function, the statistical approach to the quantum vibrational state. One can obtain the temperature-dependent eigenenergy by taking the expectation value of the eigenenergy, where we compute the likelihood to find some bond length value by taking eigenfunctions of the vibrational problem and weighting these vibrational states using the proper defining weight, the one that will define the Bose-Einstein statistic in the partition function. So we include zero-point motion. Again, the eigenenergies can be obtained from density functional theory or GW, and one will take into account anharmonicities, but still it is adiabatic. And by the way, instead of computing explicitly the quantum vibrational state, one might compute this expectation value in one very large supercell with prepared frozen atomic displacement. And this technique is used nowadays. It is the adiabatic supercell approach to the electronic structure temperature dependence and zero-point motion technique. And I will comment the shortcoming of this approach as well later, basically the adiabatic approximation. Now, in order to facilitate the thing and make the connection with the last technique that I will introduce, what if we consider everything in the framework of a Taylor series? We make for the quantum vibrational state the harmonic approximation, and we expand the eigenenergy to the second order only. So for the vibrational states, we will work with eigenmodes that are occupied with quanta of vibration. We will have the Bose-Einstein statistics. It will be much easier to deal with than global vibrational eigenstate, but this needs the harmonic approximation. And on the other hand, we expand the eigenenergy as a function of the bond length. We neglect the linear contribution because the change of eigenenergy on average will come from the curvature and not from the linear part. And we obtain this formula for the change of eigenenergy as a function of temperature. It has two parts, one that comes from the phonon occupation number, and you might recognize the 0-point motion, the 1/2 that is added to the occupation number of phonons. And then there is this coefficient that describes the change of eigenenergy due to the occupation number of phonon. This technique includes the 0-point motion. One can use the eigenenergy from DFT, from GW. It is tractable definitely for molecules, but we make an harmonic, we neglect an harmonic contribution, and we make the quadratic approximation. But it will be a workhorse to understand what is going on in the failure of one or the other methodology. This is still adiabatic. We consider that the eigenenergy immediately changes with the atomic displacement. Now, the last methodology that I want to introduce is the so-called Allan, Hein, and Cardona formalism. That is the straight second order, possibly time-dependent perturbation theory treatment of this problem. In which case, moreover, we obtain formulas for solids. Phonons have crystalline momenta. And, well, either we make the adiabatic approximation or not. If we make the adiabatic approximation, we will again neglect the phonon frequencies with respect to the electronic gap and have no transfer of energy. But we are again back to this simple formula for the change of eigenenergy with respect to the temperature that will include a sum over all vibrations in the solid. So there is a sum over the wave vector and a sum over the different modes for each wave vector. The occupation number for each phonon comes from Bose-Einstein statistic. And it is possible, again, to obtain this coefficient of change of the eigenenergy at some wave vector for the electron for some band due to the presence, modification of occupation for some phonon with some wave vector labeled with Q and some branch in the phonon band structure. What is this electron-phonon coupling energy? It has also two parts. One which will describe the specific phonon that we are dealing with, but it's not very relevant here. And another one that describes the change, the curvature of the eigenenergy with respect to atomic displacement. And here I'm using the full notation to describe this phenomena, where I have indeed phonon eigenmodes, some label for the atoms. The curvature is described properly as this second order cross derivative respect to different atomic displacement, and they are cell parameter, cell numbers, as well as atom label in this formula. If we look now at these eigenvalue changes, the curvature due to atomic displacement, we can find that there are two contributions, and I will detail this. Eigenenergies are expectation value of the Hamiltonian with respect to the electronic eigenfunctions. The Hamiltonian itself has different contribution: kinetic energy, nuclear potential felt by the electron, the Hartree contribution, and the exchange correlation contribution. One can obtain the first order derivative of this eigenenergy using the Hellman-Feynman theorem. It is easy to show that the first order change with respect to the atomic position will come from the expectation value of the Hamiltonian change with respect to the atomic position, and we have to take the expectation value with respect to the unperturbed wave function. But if we want the curvature, the second order derivative, we will have to make the derivation of the Hamiltonian once more, obtain the so-called Debye-Waller contribution represented by this diagram. But we will have also to include the change of eigenfunctions due to the modification of atomic position, and this gives the so-called Phan contribution. You here have a first order wave function, a zero order wave function here, and a first order Hamiltonian. And this is associated with this diagram. Here we have a so-called second order electron-phonon interaction. And here we have two first order electron-phonon interaction. This formula can be expressed using a so-called sum over state to give this big equation, of which I simply want to draw your attention to the fact that there are indeed two first order electron-phonon contribution, this dot here, this dot there, and there is also a denominator, the difference between the eigen energy of the unperturbed electronic state and another electronic state that is obtained by transferring some momentum to the phonon and possibly changing for a short time the energy. So this line is associated with this eigenenergy. This line is associated with that energy. There is a difference due to the phonon that has been emitted and absorbed. This is actually a formulation which is very well known in the time-dependent case, and indeed in the time-dependent case, without making the adiabatic approximation, we recover the two matrix elements, first order electron-phonon matrix element, but the denominator is changed by the presence, explicit presence of the phonon frequency. And this is actually very important in obtaining correct response, as I will show later. So in this beyond adiabatic approach, which is based on many-body perturbation theory, one obtained the so-called Phan self-energy that we will use to produce the modified eigenenergy due to electron-phonon coupling. And the simplest way to use it is the so-called on-the-mass shell approximation, but it would be possible to treat the self-energy using other techniques. So To summarize this part, I have considered different level approximation. What is the dynamics of the nuclei? Is it classical quantum? Is it important to treat anharmonicities, or is the harmonic treatment of vibration sufficient? Is there an adiabatic decoupling of the nuclei and electronic dynamics, or are non-adiabatic corrections important? And also, we might work in the density functional theory approach for the electronic quasi-particle, or the GW approach. So there are at least 4 first principle methodologies. I did not cover all of these: time average, thermal average, harmonic approximation per thermal average, and the diagrammatic approach, which is the Allan-Heine-Cardona. Usually in the 80s, it was used in the adiabatic approximation, but nowadays it is used in the non-adiabatic flavor. I have not mentioned that there is still another effect to be taken into account, the 0-point lattice expansion. Indeed, the volume changes with the temperature, and this will indirectly also affect the eigenenergy. And even at the 0 temperature, there is already a small modification of the lattice parameter with respect to a pure calculation in which the atomic would be frozen at, atoms would be frozen at their 0 equilibrium geometry. Let's look at some results. Computation of 0-point normalization theory versus experiment, and then I will also show how the diamond band structure changes with temperature. The first principle calculations have been done using the Abinit software. I will not go into the details of the calculation for phonons. For the electron, we use density functional perturbation theory, which allows to do the calculation without any supercell. Actually, it's the power of density functional perturbation theory. We have included the 0-point lattice expansion effect, and the first results that I will show are based on the non-adiabatic Allan-Heine-Cardona theory for the fan self-energy and on the mass shell approximation that actually has been shown to be better than the Dyson equation when compared to the diagrammatic Monte Carlo for the Fröhlich model. In this important figure, one has represented as a function of the experimental 0-point renormalization in milli-electron volt, going from 12.5 to 800 milli-electron volt. So it is logarithmic. The first principle 0-point renormalization also going from 12 to 800 in this non-adiabatic AHC theory. Obtaining correct experimental 0-point normalization is not easy. It can be done by 2 different experimental techniques. I do not want to describe these now. It is reviewed by Cardona and Tewald in this paper. And you can see that for 18 materials that have been studied, quite simple binary materials, I must say, except this one, the correspondence between the first principle and experimental data is on the order of 25%. This is the dashed line between here or there. And it must be said that the reliability of experimental data is on the order of 25%. So for 16 materials among the 18 that we have studied here, we see that there is a decent correspondence between theory and experiment. There is one exception here, one exception there, and I must say that this figure that is extracted from this paper was obtained without spin-orbit coupling, and that if we include the spin-orbit coupling, most of these points will stay inside this zone, but also the cadmium telluride will fall inside this zone as well. So finally, there is only gallium phosphide that is still away from the zone. So this is quite satisfactory, and it is the first proof that any technique used to obtain the zero-point normalization and the modification of the electronic structure due to electron-phonon is doing its job properly. So we are quite happy here. And now we can compare with other approaches. What about the best adiabatic approach that has been used to predict this modification, the adiabatic supercell approach? Well, we go from the blue points to the red triangles. And you see that for 5, 6, 7 of these material, actually the result is not as good as in the non-adiabatic AHC technique. And because this scale is logarithmic, going for the zinc oxide, this point, around 180 to that point, 60, means that we miss the zero-point normalization by a factor of 3. We underestimate this by a factor of 3. This is by a factor of 2, a factor of 2, and again. So it seems that there is a problem with this adiabatic supercell result. Is it true for all materials? No, no, no. It seems to work correctly. For example, for diamond, gallium selenide is, aluminum arsenide is not too bad. There are a couple of points that are still inside this zone. For germanium, it is also good. For silicon, it is also good. Actually, the adiabatic supercell approach failed to deliver the correct ZPR, but it is most often for those with large zero-point normalization and large ionicity that are these materials that are infrared active. We will ask why, and we'll answer this question why later. I want to show that in order to obtain the agreement, it was important to include the zero-point lattice expansion, which was included in the previous slide. We made the analysis of the zero-point lattice expansion for 20 materials, and simply at the level of the lattice change, it goes from 0.1%, so quite small for germanium, to 0.4% for boron nitride. So simply at 0 Kelvin, 0.4%, there is a 0.4% change of lattice parameter with or without including the zero-point motion. This cannot be eliminated, well, neglected if one wants to compare to high accuracy lattice parameter of the solids. But speaking of the contribution to the zero-point renormalization, this is also a figure in which we have gathered the different comparison between experimental and first principle data without the zero-point normalization lattice expansion or with the zero-point lattice expansion. In most cases, it is not so important, but for gallium arsenide, it is crucial. It actually brings a factor of 3 increase of the zero-point normalization of gallium arsenide. Let's now compare the value of the band gap, the full band gap, not simply the zero-point normalization, with experiment. The band gap beyond density functional theory, you know likely that density functional theory is not very good for obtaining the band gap, can be obtained by including the electron-electron interaction at the level of G0, W0 approximation, possibly with GW self-consistency, possibly including the vertex correction. I will take the study that, from my opinion, perspective, is likely the best calculation that was done for this electron-electron effect without changing the atomic position from Shishkin, Maxman, and Kresse, 2007. They obtained for a whole set of material the best band gap that they could do and compared it with an experiment. It's quite good, but there are still differences at the level of 0.1 eV to 1.4 eV by doing this self-consistent GW with electron-hole vertex. But and one can see that the biggest discrepancy is obtained for carbon, boron nitride, magnesium oxide, lithium fluoride, that contains quite light atoms. And I will argue that this discrepancy is due to phonons, at least partly. Indeed, what we did is to take this best value for a whole set of these materials with band gap going from 0.7 to 7.7 eV and represent the first principal gap divided by the experimental gap. The perfect agreement will be this line. And one can see that the G0W0 band gap, which is the first and easiest way to correct the band gap, is doing well, but not fully. It can be as wrong as 40% error for zinc oxide. It is definitely corrected by going to GW self-consistent plus electron hole, but there is apparently a small tendency for many materials to overestimate the band gap. While if we include the 0-point normalization, more materials comes to be inside the plus 4%, minus 4% discrepancy. So it is interesting, but not perfect. And then one can wonder, why are we not fully perfect? Well, I will argue that for this material, cadmium selenide, zinc oxide, zinc sulfide, there is zinc or cadmium. For material that have some transition metals, apparently there is an underestimation, but I think that these underestimation are due to the GW electron hole results. Not that the 0-point normalization is wrong, it's simply on top of something which is not really very good. Also, quite interesting at this level is to notice that, that the 0-point normalization is nearly as large as G0W0 going to self-consistent GW plus electron hole. Indeed, for this material, silicon carbide, one starts from G0W0, goes to the self-consistent value, and then 0-point normalization brings it to nearly, again, the G0W0 value. And it's the same for carbon diamond, boron nitride, and magnesium oxide. It's not true for all materials, but for those that contain light atoms, carbon, nitrogen, and boron, oxygen, here it seems quite important compared to the G0W0 going to self-consistent GW electron hole effect. So for light elements, I argue that it's not worth to do the full GW calculation without including the 0-point renormalization. Let's now try to analyze the reason why the adiabatic supercell calculation are not doing very good job for polar material. We start from the adiabatic quadratic approximation divergences, and we'll mention the math and the physics of what is happening. So if we modify on the if we focus on the 0-point modification of the band gap at gamma from Fan for some material, so you see gamma point and only the 1/2 that describe the 0-point modification. We do not look at the temperature modification. The electron-phonon coupling energy plays an important role, and I have mentioned that it has twice the first order electron-phonon matrix element, but also this denominator going from one electronic state to the other electronic state when the phonon is emitted. And this denominator can be actually very small, can even tend to 0 if the wave vector is very small and if n is equal to n prime, which we call the intraband contribution to the 0-point normalization. Such intraband contribution can diverge due to the denominator. This tending to 0 will cause likely some effect on this divergence. And will this divergence also be present when we sum over all wave vector? Well, the answer is fortunately not. When we have non-polar material, this integral, this sum over wave vector that we can show to come to this formula, because this difference between energy is governed by the curvature of the band close to the energy minimum. So it gives a q square here. When you integrate 1 over q square over a volume element, it does not diverge. In doing calculations, usually actually that was done in the 80s, one include plus I delta here to smooth the denominator. And this gave values that had to converge with respect to the imaginary part added at the denominator, but one would obtain a limit that was well defined. Here I'm taking the diamond 0-point normalization for the conduction band, valence band, or the direct gap. One has to do convergence study, one has to use large grids of points, but this can be done and yield decent value for the 0-point normalization. And indeed, one can compute as an example, the diamond temperature-dependent band structure. This is in black, the band structure obtained without allowing the atoms to move at all. At 0 Kelvin, there is a small 0-point motion, and we will go to the red curve with the width of the curve indicating the electron lifetime in this band structure. So you see that there is a small value, small change in the value of the gap, but increasing the temperature first to 300 Kelvin, then to 900 Kelvin, and then finally to 1500 Kelvin comes with a change of the gap with temperature, as well as a increased broadening of the bands, indicating the lifetime of the electrons. Then, if we try to do exactly the same study for boron nitride, which is polar, and compute the renormalization of the gap, this is what we get as a function of this imaginary part at the denominator of the expression. We obtain a divergence of the 0-point normalization due to a specific divergence of the conduction band and valence band value. So such a divergence can be actually understood. One can make a fit. It's behaving like 1 over square root of delta, and this clearly diverges. So what's the difference between diamond, that was working properly, and boron nitride? Well, one gets also a divergence of the first order electron-phonon matrix element. These two values will diverge, as well as the contribution from the denominator. Actually, each H1 value diverged like 1 over Q for polar optic modes. At band extrema, the denominator induces a 1 over Q square divergence. For non-polar mode, this is the total divergence that can be integrated, but for polar optic modes, the total divergence is 1 over Q, 1 over Q, and another 1 over Q square, so 1 over Q to the 4th power that cannot be integrated. The adiabatic quadratic approximation breaks down for material with infrared active optic mode. And the question is now whether to waive the adiabatic or the quadratic approximation. And you already know the answer because I have shown you that the non-adiatic Allein-Hein-Cardona theory gives a good agreement with the experiment, but it's not the case if, well, and the physics is explained here, the electrons do not have the time actually to follow the phonon when we look at them at the minimum of the conduction band or the maximum of the valence band, but I think I'm a bit short on time. So I will skip this explanation. And the adiabatic supercell approach succeed to avoid these divergences. For example, instead of having a gap energy that changes quadratically around the zero mode amplitude, it will soon acquire a linear part, and this is the way the adiabatic supercell approach avoids the divergence. But this is not the dominant physics, as shown by comparison with experiments. So in most of the case, and I would even argue perhaps in all cases, the non-quadratic effect is just includes the wrong physics to avoid the divergence in the harmonic adiabatic approximation. Now, this can be understood in better terms by going to the Fröhlich model, which is a simple model that was used for decades to study so-called large polarons. In this Fröhlich Hamiltonian approach, one takes one electronic band, so only intraband electronic contribution, and one phonon branch. But a part of this approximation, this is purely quadratic, and this is purely constant. And one also includes the electron-phonon coupling from the macroscopically screened Coulomb. And it happens that the zero-point normalization in this model is equivalent to the large polaron formation energy of this Fröhlich model. So the bridge is made between the Fröhlich Hamiltonian and the or treatment or first principle treatment. It actually can be mathematically formulated, but I will not go into detail of this mathematical formulation. Such a mathematical formulation can be explained in terms of, well, worked out in terms of lowest order perturbation theory, like the Allein-Hein and Cardona, and deliver a very simple relation for the zero-point normalization in terms of the longitudinal optic phonon and the so-called Fröhlich coupling constant alpha that can be obtained from basic parameter of the material, the effective mass of the electron, the LO phonon, longitudinal optic phonon, and the dielectric constant of the material. We have generalized this Fröhlich model to include multiple phonons, to include multiple electrons, degenerate bands, and anisotropic band. And we have been able also to obtain the zero-point normalization in this generalized Fröhlich approach. And it happens that in this generalized Fröhlich approach, yes, we can then plug the first principle parameters. And you see here the comparison between the Fröhlich model band gap, zero-point normalization, and the first principle band gap, zero-point normalization. We did this for oxides, for chalcogenides, for nitrides, and for trified material. We did this for 30 materials. And we see that this line being the perfect agreement, for the oxide, we obtain a good agreement between the Fröhlich model and the full first principle calculation for the 0-point normalization. For the chalcogenide, it's also quite good. And then the agreement decreases for the other materials, where the ionicity decreases as well. So this Fröhlich model captured the essential physics of the 0-point normalization when we have sufficiently ionic material. Still, such an approach has limitations, and we will analyze also the limitations of the perturbative approach, like Allan, Heine, and Cardona. I have still a couple of minutes. Because the Fröhlich model is a well-known, explored model. A lot of decades of work have been done. And in particular, people have gone beyond the lowest order perturbation theory. As a function of the coupling constant, the energy of the polaron, or the 0-point normalization energy, has been studied. And instead of, in perturbation theory, one obtained this black line, while in the quantum diagrammatic Monte Carlo technique, that is represented here, one obtained the blue dots. You see that until 6, perhaps 8, the perturbation theory results are in quite good agreement with the much more accurate Monte Carlo result. The deviations start to appear at 6. Also, the effective mass of the electron, or so-called polaron in this model, has been studied. As a function of alpha, the logarithm of the effective mass is represented here. And this is the zone where the perturbation theory is valid, but you have a divergence of the effective mass at about 6, and then we switch to another regime where we have so-called small polaron and localization of the composite particle created by the electron and the phonon. So we have analyzed this data in terms of this possible effective mass breakdown, possible formation of small polaron with finite extent. And I will pass the details here because of time limit. What we have obtained is a picture in which we look at the extent of the localization of the composite electron and phonon particle that is called large polaron. So in this zone, we have a large extent of this composite particle, and the Fröhlich model is okay. In this zone, one forms small polarons, while on the other hand, right, left, we have here weak coupling, meaning that the perturbation theory is valid, and here strong coupling, meaning that the perturbation theory is not valid. And we find for these 30 materials that for most material, the Allan-Heine-Cardona perturbation theory and the Fröhlich model are valid, but there are also materials in which clearly we are at the boundary of the validity of our approach. Finally, and this will be my last result slide, we extended such a analysis for 1,260 material. The left-right convention is different in this slide compared to the previous slide. So this is the whole set of material for which the Allan-Heine-Cardona theory should be valid, as well as the Fröhlich model. But there are also some materials where the small polarons form Allen-Heine-Cardona is not valid. And this number of material is larger for the hole polaron than for the electron polaron. Okay, at this stage, it's time for me to summarize. So I have shown that one can do accurate calculation of the 0-point normalization that agree with experiment at the level of 25%, which is decent. It's not fantastic, but still this is the representative of the experimental validity as well. The 0-point renormalization effect can be as large as the difference between G0, W0 and the full self-consistent with electron-hole vertex. Adiabatic approximation breaks down for infrared active solid. And so this means the adiabatic supercell approach is problematic for these solids, but the Fröhlich-Hamiltonian captures well the main feature of the first principle results. The dynamical effects are crucial, and there are some limitation of Fröhlich model as well as perturbative approaches when small polarons form, and this is the case for some of our materials. Thank you for your attention.